Hi everyone, it's Mrs. Griffin with Unit 6 Lesson 5 video where we're going to talk about the basic trigonometric ratios. We're going to start some basic trigonometry. So you're going to try the opening exercise on your own and we're going to look at the notes here. So trigonometry, specifically for a right triangle, which is where we're going to focus in geometry, begins with identifying a specific acute angle, either one that is given or one that we are trying to find. And then labeling the three sides of the right triangle, comparing them to the angle we're using. For the angle, a lot of times we use Greek letters. We can also use x and other variables, but a lot of times they use specific Greek letters. The most common is this, which just looks like a zero with a line through it. That's called theta. Occasionally we use alpha and beta, and rarely we'll use gamma, only if it's a very complicated picture. Okay, and then the three sides that we're going to be talking about compare themselves to that specific angle. So the hypotenuse, like always, is across from the right angle. The opposite is the angle that's across from the angle in question, the one that we would label with our theta or our beta or whatever it is. And then the adjacent is the third side of the triangle, and it's always the side of the angle in question, theta. It's between and next to the right angle and the specific angle. So if I have three right triangles here, note where our right angle is. Our right angle is always across from our hypotenuse, so we can immediately label that like we always did. So on all of these, if we cross over from the right angle, we know where our hypotenuse is. Then they have one angle marked off. Sometimes there will be a variable like theta there, or x, or alpha. Sometimes there will be a number there. It depends on the problem. So what we do is we say, okay, across from that angle is our opposite side. So across from the angle that they're identifying for us, we label the opposite. Okay. And then the side that connects that angle to the right angle, it's next to both of them, is the adjacent side. So it connects the right angle to the angle we're using. Connects the right angle to the angle we're using. It's next to both. It's adjacent to both. And that's our adjacent. And then we use those sides to create three specific ratios: sine, cosine, and tangent. Sine is the opposite over the hypotenuse. We use three letters, S, I, and N. Those are how they show up on the calculator. And then attached to it will always be the angle number or letter. And then it will be a ratio. It will equal whatever number or variable is on the opposite side over whatever number or variable is on the hypotenuse. Cosine is the adjacent over the hypotenuse. So again, we abbreviate it with three letters, cosine, and attach it to the angle we're using, whether it's a number or a variable. And that will be set equal to a fraction. On the top will be whatever the number or variable is for the adjacent side, and on the bottom, whatever the number or variable is for the hypotenuse. Tangent is the third one, and it is the name of the ratio that compares the opposite side to the adjacent side. When we are writing these, we will write TAN for tangent and attach to it the angle like all of the others, and it will equal a fraction. The top will be whatever's on the opposite side, the bottom will be whatever's on the adjacent side. In geometry, we use a phrase to help us remember that. That phrase is so, ka, toa, and it helps us set those fractions up in the correct order. If you can remember so, ka, toa, then you can set these up correctly. So now I'm going to go to the next page. For our trigonometry, every single time we start a trigonometry problem, we need to make sure the calculator is in degree mode. It is the most important part of trigonometry, and you will get the answers completely wrong if you don't do this. So to put the calculator in degree mode, you will hit the mode button, which you can see is right next to the second key. And if you look at the third line down, or fourth line down, radian is currently blinking and next to it is degree. We're going to go over to degree and hit enter, so it changes which part is highlighted. And once you do that, you hit clear. Every time your calculator is reset, it will default back to degree mode, so you need to make sure it's in, it will default back to radian mode. You need to make sure it's in degree mode before you start. Okay, so now we're going to look at the specific right triangle. This one has a 90-degree angle, a 40-degree angle, and a 50-degree angle, and they used a computer program to estimate the exact lengths of the sides to the nearest hundredth. And so these are the lengths of the sides. If we are looking at the 40-degree angle, that means that that's the special angle that I am referencing. Everything I'm talking about is in reference to this 40-degree angle. So based on that, identifying the sides, across from the 90 is always the hypotenuse. Across from the angle we're using is always your opposite. And what connects the 90 to the angle you're using is your adjacent. It's next to both. So then we will use SOHCAHTOA and set up the 3 fractions. So for sine of 40, that would be opposite over hypotenuse. My opposite is 3.64, and my hypotenuse is 5.67. And then I'm going to divide those. And to the nearest hundredth, that's approximately 0.64. Okay, cosine will be the adjacent over the hypotenuse. So the adjacent side is BC, which is 4.34. And the hypotenuse is also 5.67. And I'm going to divide those as well. And you will see that that's approximately 0.77 rounded to the nearest hundredth. Now keep in mind I am rounding everything here, so it is slightly inaccurate. Even the original values are rounded. And then we'll do tangent. So the opposite over the adjacent. The opposite side was the 3.64, and the adjacent is the 4.34. Okay, and then divide those, and you will see that that's 0.84-ish when rounded. Now, if I look at the next triangle underneath it, this triangle is also a 40-degree, 50-degree, and 90-degree triangle. And I'm going to find the sine, cosine, and tangent of the 40-degree angle again. But this time the 40-degree angle is over here. What will change is that the opposite is still across from the 40, but where it appears to be is totally different looking than the original. This has been rotated and reflected and all sorts of things. Okay, the hypotenuse is now here because it's across from your right angle. And then the adjacent connects the right angle to the angle you're using. It's the one next to both. So opposite, adjacent, and hypotenuse compared to the 40-degree angle. So for sine, the opposite would be 3.55, and the hypotenuse would be 5.52. For the cosine, we're doing adjacent over hypotenuse. So the adjacent is the 4.23, and the hypotenuse is still the 5.52. And then for the tangent of 40, you're doing the opposite side, which is the 3.55, over the adjacent side, which is the 4.23. And then I'm going to divide each and round each one to the nearest hundredth. As you can see, I'm getting 0.64, 0.77, and 0.84, just like we got on the first one. The reason is that these are ratios, meaning that they are going to be the same for all of our similar triangles. Since these are similar triangles, they're going to have the same ratios. The ratios will divide to the same thing. So because I'm referencing the 40-degree angle on both of them, and they are similar to one another, I should get the same value for sine, cosine, and tangent. Based on that concept, my sine of 40, cosine of 40, and tangent of 40 should be the exact same values here, because even though these sides are different lengths, it's similar, and these ratios should be the same. Okay, so for all triangles, no matter what right triangle you're looking at, how big it is, the sine of 40 should always be 0.64-ish. The cosine of 40 will always be about 0.77-ish, and the tangent of 40 will always be about 0.84-ish. Remember, these are rounded, and that's because they're always similar to one another. So sine, cosine, and tangent for any angle will be equal to itself no matter how big the triangle is. The triangle with these angles will always be similar triangles. And so therefore, because we know these ratios, they won't change, we can use them to find the sides or angles for all triangles of any measure. A long time ago, they figured out what each one would be exactly to the nearest 10,000th, and they made a table of it. And this used to be on our reference sheets on our Regents exam, so that you knew that every sine, cosine, and tangent were these decimals. Now that you have the graphing calculators, they've programmed these values in, so you can use just the buttons to come up with them, and you don't have to use the table to find them. Okay, you'll see how to use those values in our next lesson, but for right now, let's practice using the ratios and figuring out SOHCAHTOA and using those to find all the sides of our triangles. So, in a right triangle with an acute angle, measure theta. The sine is 1 over 2. Remember, sine is opposite over hypotenuse. So if I look at theta, across from it's my opposite, across from my 90 is the hypotenuse, and connecting theta and my 90 is my adjacent. So if sine is opposite over hypotenuse, I can fill that in. My opposite is 1, and my hypotenuse is 2. And then I can use Pythagorean theorem to find the third side. So one of my legs is 1, the hypotenuse is 2. And if you recognize this ratio, you may already see that it would be a radical 3 for the third side. And then you can find cosine and tangent by setting up those fractions. So cosine will take your adjacent and put it over your hypotenuse. So the cosine for theta will be radical 3 over 2. And tangent will take your opposite and put it over your adjacent. So tangent of theta will be your opposite over your adjacent. Also keep in mind, like everything else, we can't leave the radical in the bottom, so I need to rationalize this. So this becomes radical 3 over radical 9, or radical 3 over 3. Same thing for number 2. We have a right triangle. The tangent of theta is 5. So if I draw a right triangle and I put theta in it, I'm going to put theta on top here so that you see that it doesn't matter where it goes. Across from your theta is your opposite. Across from your 90 is your hypotenuse. And next to both theta and 90 is your adjacent. If the tangent of theta is 5 over 1, remember that tangent is opposite over adjacent. We now know that the side opposite theta is 5. And the side adjacent to theta is 1. I can use Pythagorean theorem to find the hypotenuse. So 1 plus 25 is 26, and the square root of 26 is just radical 26. That would be my hypotenuse. I can now use that to find sine and cosine. So the sine of theta, remember, is opposite over hypotenuse. So my opposite was 5. And my hypotenuse was radical 26, and then I can rationalize this. I'm going to multiply by the same radical. I'm going to do a radical 26 because I can't think of anything smaller to get a radical 676 on the bottom, which is a perfect square. It makes 26. And then on the top, these cannot be multiplied, so just next to each other. And then the 26 cannot be simplified any further, so that is done. And cosine, same idea. To find cosine, we're going to put the adjacent over the hypotenuse. So the adjacent side is 1, and the hypotenuse is radical 26. And just like the sine, we're going to have to rationalize it the same exact way. 1 radical 26 is just radical 26, and then we get our same thing here on the bottom. And so our cosine is radical 26 over 26. On to number 3, similar setup. We're going to have a right triangle. Put theta in there somewhere and label your sides. Across from theta is opposite, across from the 90 is the hypotenuse, and next to 90 and theta is the adjacent. Label what they tell you. The sine is radical 5 over 5. Remember that sine is opposite over hypotenuse. So opposite is radical 5, hypotenuse is 5. We can now use Pythagorean theorem to find the missing side. A squared plus b squared equals c squared. Remember, a squared and a radical cancel. Subtract your 5 from both sides and square root. And then I'm going to simplify this. This becomes 4 and 5, a 2 radical 5. And so my adjacent side is 2 radical 5. And now I can set up both. The cosine will be the adjacent that I just found over the hypotenuse, and that's as simple as that gets. And the tangent will be the opposite over the adjacent. And I'm just going to divide those and make this 1/2. And that's both of them. And we will do the rest in class, so I will see you then.